Welcome. Let's take a look at an introduction to vector-valued functions. Let's start with a definition. A vector-value function is a function of the form vector r of t is equal to an x component f of t and a y component g of t, and that would occur in R2 or the plane. Additionally, vector r of t could be f of t in the x component, y component g of t, z component h of t, and that could occur in space, or R3. In both of these cases, the component functions f, g, and h are real-valued functions of a parameter t. So you might be wondering, what does r of t do? Well, r of t is a vector, and its initial point will lie at the origin. And the tip of the vector r of t identifies points along a curve. In this particular image, we have the vector r of t on an interval for t running from a to b. At the left endpoint, we have the point f of a, g of a, which is the result of evaluating vector r of t at t equals a. And at the right endpoint, we have f of b, g of b. That point is the result of evaluating the vector r of t at t equals b. Let's take a look at what this looks like. In this animation, we can see the vector r of t tracing out and identifying points along the curve here in blue. And notice that the vector r of t, its initial point remains at the origin, and the tip or terminal point of vector r identifies points along the curve. So what we're going to do is look at an example. We'll be sketching the curve parameterized by the vector r of t equal to 1 minus t for the x component and 2t minus 1 for the y component. And we'll be doing so on the interval from -2 to 2. So we'll start by picking values of t, evaluating r of t, and using that vector r of t to identify points along the curve. So let's start with t equals -2. If I evaluate r of t at t equals -2, I get 1 minus -2, which is 3 for my x component, and 2 times -2, which is -4, minus 1, -5 for my y component. So I have a position vector with a horizontal or x component of 3 and a y component of -5. So I have a position vector looking like that. At the tip is a point on my curve, and that point occurred because we evaluated our vector valued function at t equals -2. Continuing on, let's do t equals -1. Evaluating my x component, I get 1 minus -1, which is 2. And for my y component, I get 2 times -1 minus 1, so that's -3. So I have a position vector with a horizontal component of 2 and a vertical component of -3. So pointing right about there. So at its tip, there is a point that corresponds to t equals -1. Continuing, t equals 0. My x component is going to be 1 minus 0, so that's 1. And 2 times 0 minus 1 for my y component, so 0 minus 1, so -1. So now I have a position vector of 1, -1. So there's my position vector. At the tip is a point on my curve, that is t equals 0. Now for t equals 1, 1 minus 1 is 0 for my x component, and 2 times 1 minus 1 is 1. So my position vector for t equals 1 is 0, 1. So it looks something like that. At its tip is another point along my curve, and that occurred at t equals 1. And we'll do one more, t equals 2. When t equals 2, my x component is 1 minus 2, so negative 1. When t equals 2, my y component is 4 minus 1, or 3. So I have a position vector that is negative 1, 3. So looks something like that. At its tip, another point along our curve, so t equals 2. So now to sketch my curve, I simply connect the points along the curve. And it generally looks like I have a line segment here. And I'll go ahead and erase my position vectors because they're not really part of the curve. They were just useful in helping me identify the curve. And so, oops. So our curve looks something like this. And notice it had a direction. Those points we plotted as t increased, so our direction is upward and to the left. So let's look at one more quick example. We're going to sketch the curve parameterized by r of t is equal to cosine t comma sine of t for the interval from 0 to 2 pi. You may recognize this as being a circle. You may not. So let's go ahead and pick values of t that are easy to work with these functions. So we're looking at the interval from 0 to 2 pi. So let's start with 0. Cosine of 0 is 1. Sine of 0 is 0. So we're going to have a position vector 1, 0. So it's going to look like that. And there will be a point at the terminal end, and that corresponds to t equals 0. Let's pick another convenient point. Let's go ahead and do pi over 4. Pi over 4. Cosine of pi over 4 is square root 2 over 2. Square root 2 over 2. And we can go ahead and estimate those. And that point, that vector would be right about there. About square root, or about 0.7, comma 0.7. So right there, we're going to have t equals pi over 4. Choosing another value for t, let's go with pi over 2 this time. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So our vector, our position vector this time is 0, 1. So something that looks like that. And at its end is a point on our curve. Now I'm going to skip 3 pi over 4 and just go right to pi. Cosine of pi is negative 1. Sine of pi is 0. So my position vector would look something like this. And point on our curve at the tip, and that's due to t equal to pi. I'm going to go ahead and jump to 3 pi over 2. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1. So we have a position vector looking like that. At its tip is a point along our curve, and that's due to t equals to 3 pi over 2. And then if I go to the right endpoint of our interval, 2 pi, then cosine of 2 pi is 1, sine of 2 pi is 0. So we come back and we have, again, this position vector that is 1, 0. And that corresponds to t equals 2 pi. So our curve is a circle, and it looks something like that. and it's being drawn out in the direction of increasing t, or in the counterclockwise direction. I'll go ahead and remove our position vectors so that we can see our circle. And there we have the sketch. I hope you find this helpful.